Alright, so here's the tension right here. It's pulling up on the foot. Here's the normal force, same thing, up. And here's the force of the bone, and it's going downwards on the foot. Alright, so here's the angle in between this triangle. I tried my best to make it look like a right triangle. Alright, here's that angle as well. Okay, so because everything is in equilibrium, we can use both of these equations, both for the force and the torque. Okay, so they're both going to equal 0. The foot is not moving. So in the x direction, the x component, we have negative F sine B. This force right here is a negative force because the tibia bone is pushing down. It's exerting a negative force down on the foot, and it's sine B because that is the x component right here, opposite. So sine T cosine A, this is the tension. It's pulling it up, tiptoes up. So the foot up, I should say, and it's cosine because it's adjacent. That's the x component for A. Now for the y components, we have negative F cosine B. That's right here. That's a y component, adjacent. T sine A, it's opposite. That's y. N is also a y as well. So now I'll put it in this equations. For y, I expanded the n into a half mg because on both, the weight is distributed evenly on both feet. So that means half of the weight is on one foot, the other half on the other. So that's why it's a half mg. So now that I got the equations in order, now I'm gonna go ahead and apply my torque equation. So and I pick my torque right here so that I don't have to worry about this force, the torque of this force. I only have to worry about the tension and the normal force for torque. Okay, so for the torque of the tension, it's going to end up being negative B T sine A. Okay, why? Because the torque is going into the plane of the paper, so that's why it's a negative torque. But also, okay, so here's B, and this is sort of like the radius from the end of the foot to where the muscle attaches to the bone, and that's 0.06 meters, and that's going to be multiplied by the perpendicular force, which happens to be this right here. That's why it's sine, because it's perpendicular. You can imagine an imaginary x dotted line and a y dotted line. Okay, so a horizontal dotted line, it's not parallel, it's moving this way. So that's why it's negative B T sine A. That's why it would be T sine A. Now, the normal force for the torque, a half mg, which is the perpendicular force. It's the perpendicular force because imagine a dotted line here, horizontal, it's up, it's perpendicular, and S represents this radius from the bone to the end of the foot, and that's 0.048. Okay, and also that torque is positive because it's coming outside of the plane of the paper. It's outside of the plane of the paper, so it would be a positive torque. All right. Now, applying this equation to my torque, add them together, set them equal to 0, and now I can isolate the tension. Okay, and this is how I isolated it. This is the math for it. A half 75 multiplied 9.8 multiplied by 0.048 divided by these numbers, and the tension is 489 newtons. All right, now, okay, so that takes care of our tension. Well, now we need to find the magnitude, and let me flip it back over. Now we need to find the magnitude and the force. Well, I guess that is the magnitude, but now we need to find the direction, the angle, and the magnitude of this force here. So we want the force and this angle, which is unknown. So, taking a look back at these, the original two x and y equations, I rearranged them to get the forces by themselves. Okay, So, well, to isolate them, okay? Now they're isolated, and now I went ahead and divided these two equations. So once I divide these equations by each other, this is known as the cotangent of B. Okay? And I'm trying to find the angle out right now. So cotangent of B is also equal to this. Now, but we want to find the angle. So it's the inverse of the cotangent, and that's how it would look. So once, and here are the numbers. That's just the math for it. That would be the answer. You know that cotangent is 1 over the tangent, and it's this, and it is 33 degrees. So now that we have the angle, now I can go ahead and solve for the force. Okay, so the force for, let's see. Okay, so in this equation, we want this force. So once I get that force, I can go ahead and say, oh, I'm sorry, this force. This force right here is what we're looking for, okay? So once I do that, I can substitute this angle into this equation, because we use that equation, so now I'm going to find the force. So once I do that, I just plug in the number since we know the tension and now the angle. And the force is 717 newtons.